In this video, we are going to be solving a problem on the board which is having a series of resistors and currently through them. Now this problem is based on the Kirchhoff's law, okay? So we are going to be applying the Kirchhoff's laws to solving this problem. Now we've also done a video on Kirchhoff's law. So if you don't know the definition and how they are being applied, we've done that in our other video. So you might as well want to watch that video to gain a good understanding before coming to attempt this problem. And for those persons that have watched it, here is a chance for us to practice a problem on it, okay, and see how well you've understood the concepts. Now the question says find the currents in the figure above. To do this, we are going to apply the Kirchhoff's law. You notice that the currents they are asking us to find are simply I1, I2, and I3. Now I1, you notice, is coming from the source voltage, okay, going through the loop, passing through 4 ohm, which means the current through the 4 ohm is I1. When it gets to this junction, okay, it splits. Some parts go downward, some parts go upward, of which the one going upward is labeled I2, which means the 5 ohm resistor has a current of I2 flowing through it. And then coming here again, I3 goes through what now? The 9 ohm resistor, okay? So it is that easy. Here we're having a series of loops. We could as well cover this to have a loop which is 4, 5, and then the 6 volts, okay? This is a loop. We could as well take this one out. This is also another loop we could consider, or we could consider maybe taking 5 ohm out and we're left with this and this, okay? So that is a loop. And then most importantly, also the junctions, okay, in which we're having the currents. So having I1 here, for example, we're having I2 and having I3. You notice that I1 is going here. When it gets here, it splits into I2 and I3. And then from our other video, which I explained the junction rule, I said that the total current that is going into a junction is equal to the sum of current that is leaving, okay? It is that easy. So for this case, I1, we are going to have I1, which is the current that is entering, okay? Current that is entering junction, I1 is entry. It splits into I3 and I2. So it is equal to I2 plus I3, okay? We can as well rewrite this as I1 minus I2 minus I3 equal to 0, which is equation 1. We're going to call it equation 1. Remember I said we could as well state the KCL rule as the algebraic sum of currents in a junction is equal to 0, which is also just derived. Okay, now which of these loops do you think we can also consider? Let's first of all consider this. Since we know we are looking for TV unknowns, I1, I2, and I3, it means we should be having TV equations now, right? So let's consider this loop. Okay, let's consider this one. Okay, so we are taking this direction and we are assuming that all the currents in this loop, they are going what now? In this direction, which should be what now? Positive. So we're going to consider this loop. Okay, it means that the voltage across this guy moving in this direction, what will be the sign? Okay, you don't have to guess, we've already explained it in the other video. Now since current is moving, I2 is moving, that is, it is entering this resistor. Remember we said if you are going in the same direction as the current, which is the direction I will pick, if you are going in the same direction as the current, what will happen? The voltage across the element, which in this case is a resistor, the voltage across the element will be what? Negative, because we are going in the same direction as the current. So I2 is entering this guy. It means what now? It is moving from a higher potential difference to a lower potential difference. So since we are going in this direction, it will be what now? A negative. Okay, so for a clockwise direction, okay, we are taking the clockwise direction. Let's call this loop 1. Okay, let's call that loop 1, and let's call this loop 2. Okay, clockwise direction for loop 1. What then are we going to get? We are going to get this voltage, okay, voltage across the 5 ohm resistor. I'm going to write it as V with a subscript of 5. Since we are going like this, remember it is what now? Negative, Abi. So we have minus 5, okay? Coming here again, the current is still coming here now, right? Since we took this one as our direction, the current is still coming here. It will get to this point and then go into this branch, falling back to the series. But then the current through the 9 ohm resistor, notice this is I3. This is I3, it is coming like this. So it means here is positive, here is negative. Current has to move from positive to negative. But then the direction we pick is now opposite to this one, right? We are taking the clockwise direction. So it means we are coming like this. When we get here, the current is going in the opposite direction. Oh. So since current is going in the opposite direction, it means we are moving from negative to positive. That means our voltage here has to be what now? Positive. Since we are moving from negative to positive, how do we know we are moving from negative to positive? The current is in this direction, okay? So it means the voltage across this 9 ohm is going to be positive. So I'm going to have plus V with a subscript of 9 and then is equal to 0. Why is equal to 0? There is no other element here to account voltage for. Okay, so it is that easy. Now from here we know that V is equal to IR, so we're going to have minus, what is the current across the 5 ohm resistor? That is I2, so we have I2 times R. What is, okay, let's just write it as R across the 5 ohm resistor plus, okay, I'm going to write it as a subscript of 5 so you know it's what now, the 5 ohm resistor plus, now for the 9 ohm resistor, the current here is what now, ITV, okay, so the current here is ITV times the 9 ohm resistor and this is equal to 0. Now let's substitute, okay. R5 simply means R is 5, so I have minus 5 I2 plus R9 is 9, so we have 9 I3 and this is equal to 0. Okay, I want to rearrange this equation so that it will look exactly like this one. Okay, it's already arranged, so we have minus 5 I2 plus 9 I3 equal to 0. Okay, when you're writing the final one, we could as well okay, let's write it. This can be written as 0 I1. Since there's no I1 in this equation, it means it's 0. 0 I1 minus 5 I2 plus 9 I3 is equal to 0. Okay, this is what we're going to have. 0 I1 minus 5 I2 plus 9 I3 is equal to 0. Okay, so that's easy. So now we have two equations. Okay, the next thing we are going to do is create a third equation. Now, how do we create the third equation? We've already considered the first KCL, which is the current. Okay, we've considered this loop. So now let's try this loop. Now I told you we could as well cover this one and take 4 and 5, okay, down to 6 as the loop, or we could as well cover this one, take 4 and 9 down to 6 as the loop. Okay, so anyone you want to should get the same thing except you're making errors in your calculation. So I'm going to cover 9 in this case to take 4 and 5 to complete the loop. Okay, so here is the loop. Okay, now we're starting from here. Notice that this line is longer than the other one. It means current is moving from the right hand side to the left hand side. That means here is negative and here is positive, right? Or rather, current is moving from here to here. Here is positive, here is negative. Okay, so what direction are we going to take? Let's still take the clockwise direction. Okay, clockwise direction to be positive. So I'm moving from the negative side to the positive side. And remember, since we're moving from the negative side to the positive side, that is an increase in potential difference. Okay, an increase in potential difference is simply telling us that we are going in the opposite direction of current. Remember, since here is positive and negative, it means current is moving in this direction. And if we are going in the opposite direction of current, it has to be positive, which is an increase in potential difference. Okay, so we are then going to have 6 ohm, the 6 volts. Okay, so we are going in this direction, which is the clockwise direction. So I'm going to come here and write still for the clockwise direction. Still for the clockwise direction. In this case, we are having loop 2. Okay, still for the clockwise direction, we are going to have the 6 volts, which is positive. It is positive because we are choosing this direction. Okay, now when we get here, what do we encounter? We encounter the 4 ohm resistor. Okay, the 4 ohm resistor, and current here is what now? Moving from here to here. Here is positive, here is negative because current is flowing from here to here, right? So it means when we are going through this resistor, when we enter here, we get a potential drop because here is positive, here is negative. Okay, so when we enter, it becomes what now? A potential drop for the 4 ohm resistor. That becomes minus V4. Okay, because there is a potential drop. Okay, and then when we continue, when we get to this place, we notice that the current is also moving in this direction, of which gives us another potential drop. So we're going to get what now? Minus V5, right? So we are moving from positive to negative. That is a potential drop. So you have minus V5 equals what now? 0. We cannot substitute to give us 6 minus this is what is the current across V4, that is I1. So we have I1 times, let's just write it directly. The resistance is 4. Okay, or let's write it as R4 first, minus the current across V5 in this case is I2. So we have I2 times R5 equals 0. Now let's substitute. We have 6 minus R4 is 4, so you have 4I1 minus R5 is 5, so you have 5I2 equals 0. Okay, we can as well rearrange this. Let's rearrange this. Okay, this can be rearranged as minus 4I1. You notice I always want to write the I1s first, okay, because of the way I rearranged all these ones. It's a simultaneous equation. So you have minus 4I1, okay, minus 5I2. Okay, there's no I3, so we can write plus 0I3 equals, taking this to the other side gives you minus 6. Now this becomes equation 3. So solving the equation simultaneously, I'm going to rewrite everything. Okay, so the first one is I1 minus I2 minus I3 equals 0, and this is equation 1. And then here's equation 2. 0I1 minus 5I2, 0I1 minus 5I2 plus 9I3 equals 0. This is equation 2. And then we'll have equation 3, which is minus 4I1 minus 5I2 plus 0I3 is equal to minus 6. This is equation 3. We are then going to solve these three equations simultaneously by using a calculator. So you have 1 minus 1 minus 1 0 0 minus 5 9 0 minus 4 minus 5 0 minus 6. Okay, so this gives us I1. This means that I1 is equal to 0.83 to 2 decimal place in amperes. I2 equals 0.53 amperes, and then I3 is equal to 0.297 amperes. Okay, so these are the answers to the problem that we just solved. Okay, I1 is 0.83, I2 0.53, I3 is 0.297 amperes. Okay, and that is how a problem like this is being solved. In our next videos in our playlist, you find more solved exercises. And then if you have a question, do it to put it in the comment section. And then you have a topic you'd like us to talk about, also write in the comment section. And don't forget to give the video a like, and click on the notification bell so that when new video is being uploaded, you'll be one of the first persons that will get notified. And remember, you can't click on the notification bell without subscribing. Okay, so do it to smash that subscribe button, and also share with your friends. Do not let me alone. See you in the next video. Bye.